Okay, good evening team. I'm back here. This time I just want to continue with where we stopped. We are done modeling, we are done loading, we did analysis, and we look at the analysis output. Now we need to do the design. Now the design, I think for the software, I think the most important one, we have how many design to do here. We have the girder, we have the diaphragms, we have the deck slab, and then we have the pier cap, we have the pier support, you have the collar beam, and you have the pile system. So in real sense, when you're doing a design and you're providing your report, you must have. So this is now where you have done your global modeling globally, you have run your analysis, is depicting the true behavior of your bridge, and so from here you should be able now to pick each of these elements and design. I can quickly look at the design of the pier, the pier cap. We can do design of pier column, we do collar beam and the rest. So where do I start from? I think let me start with the steel composite girder. So for the steel composite, normally the best thing, I can remove the 3D thing, and then I'm interested in getting the deck system, and then activate the deck. This one has got these dummy slabs and the rest, so it's going to interfere. I want only the girders to appear for the design. So I come to section and try to activate. I put my composite. When I double click, it highlights then there is the hogging part. I think that is composite 2, composite 1. So I have also, I just make it, that's the member, and these are the ones. So I'm now left with only these are the girders, you can see. So there are 16 numbers. I've removed the cross bracing, the diaphragm. I'm only left with the composite member. You see the slab and you see the steel girder. You can't see the shear connector, but it will appear when you start design and you do design. It will appear in your output, and you will see how beautiful the shear studs are. So this is what. So now we know where. So I'm interested in the bending area, the shear area, and the hogging area. So what I'll do, I can pick this area. I highlight something here. I highlight along the shear, and then the bending where I expect a lot of stresses to happen. So having done that, I go to the design with the section interface, which is now, you see, we have steel beam, we have steel design with to BS to Eurocode 3, and there are different types here. You get it, different codes or practices. Then RC bridge, you know. Then you have this one, and then there's the composite design here under Eurocode 2. And I think that is what we have. We don't have BS 5400. We have, I think, Eurocode 2. So with this, I'm able to start the process of design. Remember now, the section specification and definition has already been done prior to modeling. So here now you see these are the conditions that you need to fulfill. We do our design parameters. I've already highlighted members to give me sample design. So this, if you are well versed with, you can check this design to Eurocode. Now we can either do recommended or French, but I think we'll do recommended or update by code. These are a factor of safety that somehow, if you read now from our literature, you can get all these partial factors: concrete, reinforcing steel. There is a reason why concrete has higher factor of safety than steel. I think at your undergraduate they always ask that question for you to explain why the factor of safety of steel is less. So please, the thing continues, look at it. So these are the ultimate limit state and serviceability limit state checks that will be done. So I think here you say okay. Then but if it wasn't there, normally when you do, sometime all these are unchecked, so you check all these box to make sure they're all done, are all taken care of by the software. So the design material, this one you have to make sure they're all the main bar, everything is picked here. So reinforcement detail also under Eurocode, I think we are doing class B, so all are now there. When I say modify, you see, even the class B of main reinforcement appears. So we are done with that. And then your longitudinal reinforcement, I told you, we're supposed to have done it. You can either do it at the modeling stage, or you do it when you're doing design. So with that, I come here, I make sure the guidelines is basically you're specifying a cover. If the cover is 0.025, it will appear. If it is 0.004, that's what appears. If it is, so you have to make sure you get it from Eurocode. Exposure condition, you get the right cover for the top and bottom, but normally for modeling you can't give difference. I think this is now issue to do with the software engineers. They need to give different so that you are able to get different cover. The top cover and the bottom cover could be different, but here it is like uniform. So putting input B will allow us, method B will allow us to do the number or the center. So being a 2 meters, and I assume that the spacing is maybe 200 for a start. So it will be for a 200 could be 10, then 11. So I have a 11 reinforcement. I want the software to include the H bar, and I believe I'm going to use 16 mm diameter, and then I'm using part 2. So I think yep, we are doing that, and then I come and then highlight. Oh, sorry, I think I didn't want it to. Okay, fine. So they are picked outside, so I put here, I put there, I add, I do the same here, I add, then I apply, then I do the second one. The first one I've done, then the second one is the same dimension, everything. So I do my reinforcement definition, I add, I do the second one, the bottom one, I add and apply for it to be visible. They're all here, so I close. Then I go back to the command tracking, continue coming down. You have the defined flange and web. Here it's already defined longitudinal stiffeners. When the steel plate girders are deeper than certain what, then you need a longitudinal stiffener. But this is on I think 1 meter, 1.2. We are about 1.2. That is not as deep as we could, but still, if you want, you can specify. But we need to specify the design position. Normally we check position I, or you can do I and J. Then you also add and replace. You just do add, then make sure it is activated. Then you go back, and then you make sure the position of output is also taken care of by the software for it to be able to direct the output where it's required. Then we need shear connectors. Now this is now where I told you shear connectors. If you go to BS5400 part 5 or even Eurocode, I think EN 1994 or part 2 or something, you are able to see the spacing requirement, the minimum spacing, the H distance, the N distance, the diameter, so all that, the connectors, how many do we need? I think here I'm going to say let's put 3. It depends. You may find 3 is going to be too much. It's going to give you the ratios less than 1.5, so you can adjust to 2. Tensile strength, I think it is we need to calculate, but for now I can use a 450. And then the diameter I can use 0.022. I think that's the maximum one. Overall height I can use 0.125. Please check the requirement that the heights are all given. This is just demonstration where we can do this, but also it's not far from what I'm giving. So center to center, if the width of the flange is if the width of the flange is 300, and I have 50 millimeter end distance to the center line, I'm left with 2, and so the spacing will be 100 100. So there are two numbers. So center to center, it will be 0.1, and then the spacing. The spacing they are meaning here is now the spacing in the longitudinal direction along in the line of the shear. Remember we were talking about shear there. So in shear, I think let's say the spacing is 0.15 for the start. Then I can now say, having put all this, I say apply. So then you can still reactivate to make it active. Then I move to the next command line. After shear connector, I go to transverse stiffener. Transverse stiffeners, now also you need to understand what are the stiffeners. You see, we need to know, I think this is something I forgot to talk about. That's one of the elements when you are dealing with plate girders. You need to also, stiffeners help a lot in improving the shear response of the plate girders. And so it is very important that we know the spacings and the sizes matters a lot. So for this case, I think we need to have write up something on the stiffeners where they are the detailing to appreciate. So the height of stiffener you need is when the bottom of flange to the bottom of top flange to the top of the bottom flange is where we expect to have the stiffener. So if you have a 1.5, 1.25, and then your top flange is 40, and the bottom top flange also is 40, that will mean that your HT will be the 1250 minus 80. So you're going to get something like 117. No, 116, 117. Yeah. So it's going to be 1.17, and that is the interior of the internal dimension of the flange, the bottom flange and the top flange of the girder. The thickness normally rule of thumb is 0.0 is a 12 millimeter, but you keep checking depending on the response and other thing. You may find 16 millimeter diameter is okay, or even 10. Because yep. So I think let's for the software we can still do you can still do your 12. But you may find 12 doesn't work. You need 13, you need 14 millimeter thick. Sometimes you also need what they call stiffeners, end bearing stiffeners over the support, over pier support and over abutment. And bearing stiffeners take point load from the reactions, and therefore if you don't handle it very well, it also undergoes buckling. So it is very important. The pitch, this is the spacing. We can say let's do 1 meter or even 0.5, depending on if 1 meter is too much, it will fail. So you iteratively handle. But if you are exposed to much of the design and you now know, you can start with slightly closer spacing and then you adjust to get what you want. So I think that will be that, and then I say apply, and then we still get the active one. We go to the next command line. The end the stiffen at the end support. At the end support, normally what we do, we first look at the nodes. I want to know, yes, so it is what is 3, 5, 7, 9, 11, 13. Then so you have 3, 5, 7, 9, 11, 13. What about this end here? Here you have you have 4, 6, 8, 10, 12, 14. So this you have to, because this one they're going to have bearings. They are going to have bearing. They are going to have bearings. No, bearing stiffeners at the end, and because this is over basically the support, the bearing stiffeners tend to buckle, and you may find the thickness need to be improved, or you can put the same but 2 in numbers. But for now we can still leave it at 12 millimeter diameter. It may pass. So what we do, we come and we specify the transverse at the end support. So I come and click my 4. I start with 3 actually. The 3 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Basically, you saw the 4, 6, 8, these are the 2 to 2s and also 2 to 2s. So in total, you're up to 14 actually. So not leave one. So out of 14, so I think this is 14, that is 13. So rigid end support, that's the same height, that is 1.17. The thickness, I'm leaving it at 0.15, and then a slight eccentricity of 0.25 millimeter. Then I add, and then after adding, I'm done. It's already taken care of by the software. So I have done design parameter, all that up to the end. So now, the reason why you need to learn a bit of steel composite plate girder in specific, the issue of designs of plate girders have a lot to do with those. You can see the load application, the lateral torsional buckling data, the damage equivalent factor, fatigue load. All these things are plate girder. They are part of the design theory that you need to follow. It is very, very important that you follow, and then now when you are modeling this, you refer to your notes, you refer to the literature, and you are able to get information, right data to input, so that you don't get garbage out. So that is very, very important. The type of loading here, you see, if you go to the codes and other literature, it will give you all those the behavior of the load application and the girder type. They give you the types of load application, type A, type B, and type C. All are given here. So and what are those types of loading? The definition are all given. For now, let me just give you type B loading. If you go to the literature, it will actually give you what it's all about, and then you have to, I think I will get that and we share. So I think that it is 0.35, and then the spacing, I still give you the same spacing of my stiffeners. Of course, they vary. You have to check on the. I think if I had that literature quickly, I would have actually looked at these types of load application, type A, B, C, and then giving you these other factors. They are in the code. I think what I'll do is let me get the literature and share with you guys, and then we move at. So we have to now. You see, now I went too far. Now I need to remove the note. I need to come back to get that back, and then okay. But now what do we do? I'm just trying to highlight closer to where I was working. I don't want to go into the details of what. So for the shear, I think this is where the shear is. And then our support. Okay, our support we have this. Our support we have that. You know, for a continuous member, our support, the top flanges are in tension, while the bottom flanges are in compression. While mid-span, the bottom flanges are in tension, while the top flanges are in compression. That is how you look at the thing. So it is very important that we get almost all this, and then we try to model not to. So I can just randomly select and then see. So I can now apply the type of loading, and then I can now move to the lateral torsional buckling data. Here you need the distance between the springs. Now that is we had the torsional buckling members are the cross frame and the cross diaphragms, which were spaced. Each of these is 30 meters, and I think we have 5 span. 5. If it is it 5? I can do this, and then I'll try to see. 1, 2, 3, 4, 5. If it is 30, so it is 6 meters. So that means it is the spring constants as that's the connectivity at the to connect and simulate that. Then the spring stiffness around 50,000, but we can look at the actual one, could be 100 or something. There, I think this is from, I told you to look at Midas software tutorial. You will get some. So the alpha from the code around 4, and this is the spacing of the between the parallel beams are basically 2 meters. So we can now we enter that, and then so these are some of the parameters that you need. You pick from the literature, from manuals, and then some best practices, and you feed in, because at the end of it all you want to have this bridge, this to design, and should be more or less similar to if you were to design this by making reference to your code to practices manually. That's the good thing, that even if you go wrong, but you can still have control and go back and get it right, especially in terms of factors we are looking here. So that the damage equivalent factor, if you look at the literature, here is about 0.75, and here is about 0.5, which is the lambda, this one factor for the traffic on other lanes. So this is now where you read about the traffic volume, traffic flow on across the bridge, and then the number of lanes and the incoming and the outgoing. So very important. The factor of the traffic volume, they are all given, and you pick, and then we use that. So that is the factor we consider. Then we now come to damage equivalent. We have looked at fatigue load combination is already given automatically. These are the load combination list. The fatigue they already picked on this side, because we defined our fatigue load already earlier on at the loading stage. So now at the end of it all, now you come down, the serviceability load combination, they already been selected, the frequent, the characteristics, and the quasi-permanent. From your EN2 and the rest of it, and even from BN 1991 EN, BSEN, you should be able to get to know the different load combinations and the characteristic behavior, the serviceability limit state loading requirements, where we do the characteristics loading, quasi, which is the dead load, and then the frequent with additional live load. So some of the things you picked, then now you come to design. Now then you are done. You ask the computer to design, having input all your data, which are basically factors that are required, because the rest are already been transferred from your analysis. All you need are which require a bit of reading, and I urge you guys to read. You're going to get all these factors, and also from the use of internet and AI today, you should be able to get something very well, and so that when you input, the design doesn't. My only problem is modeling. Once you do accurate modeling, accurate loading, proper boundary condition, design now become easy. You just have to follow the procedure and make sure you get the right. That's why they always say design is basically use of reference and code of practices, where you just relate to what is required, and you're done. So basically this is how the design is done. Now it is running the design, and the output will come, and we check. So the design is done. All we need is we are going to go to the same design. Now you see this design print result was not active, was deactive. So now it is active, mean I can now print a report, or I can come to design. Now you see bending resistant, resistant to vertical shear, resistant to lateral torsional buckling. So these are the resistant. So you want to see that the applied load, the action effects, do not exceed this resistance. So once they have all passed all these limits, therefore you find that the design is okay. You can now go and try to do optimization, because they also give you what we call the ratios. Maybe the applied to the resistance, the ratio could be 0.4, 0.5. You can still take it to about 0.75 to give you a bit of a balanced design. So what would be the bending resistance of these girders selected? Now you can see it has given you, but some areas are indicating red. It means that what are not passing, but majority are what are passing. This is good indication that when you do some slight improvement, either you improve the flange thickness, web, but web normally is for shear. Flange thickness is where sometimes it helps. So if you have read about the steel girder behavior, you will know which part of the girder plays a bigger role in tension effect or tension resistivity or resistance, and then which one tend to play better effect in resisting shear. Is it the flange? No, is it the web or the flange? You can design both web and flange to take on moment, or you design the top and bottom flanges to take moment while shear is taken up by the web. Those are things you can do. So this is the first one you can check. Then all the requirements are given, and then you can go to the next one, that is shear, vertical shear. You have seen shear seem to have passed all. You don't see anything red. Now that means the section you have specified is passing shear. The shear resistance is very, very high. So that is something you appreciate. Then we can also check. So now you're checking the resistance to lateral torsional buckling. Definitely during construction, you can see some areas are exceeding the allowable. I can see one exceeding the rest, like 0 but this already 10 something. So it's minor adjustment you need. So the choice of the steel we have given is not very far to near the actual or what is feasible. So then you can go, after that you can now look at resistant transverse forces. Yeah, some elements need, and it can give you even the element which is affected, and also you see the factors are exceeding 1. Yeah, the interaction ratios should be less than 1. So here are interesting area. You can even see you could be over the support or somewhere. You check. Then now you check all that. Now the longitudinal shear. I think issue to do with shear seem to be passing all longitudinal shear, and then now we are going to also look at fatigue resistance. I think you see. So it means the element we picked, the shear start of 22 millimeter diameter, 450 MPa, what seem to be passing, and the girder seem to be fine. So all in all, and then the stress limitation. Your stresses are all passing. You see the stress limitation, the bottom stress and the top stresses. I think they're all passing. So you can easily look what is now remaining is longitudinal shear flow. I think all that the shear flow between the flange, top flange and the slab also all are here. So this is what you always look at, and then you tend to check. So I think from our checks for now we are comfortable that whatever we have done is more or less fine. With these few adjustments, you can go and do that. So you can now print if you want. You print the result. You can print your result, and then you see that gives you a better presentation of the report. It is Excel based, not that which is giving in Microsoft Word. This one will blow you up. You don't even need to save it anywhere. You can see. So immediately you see that, and then I push it a bit here. So now you see it's giving each element. I chose few, but it's going to give you all. You see, it gives you the member information, design code, section properties, materials, all the way down to the length, factors. These are factors given, and then you see now here, use whatever you specified is exactly what we have now here. You have a 340 millimeter thickness, 300. All these are given. The intermediate stiffeners are not shown here, but they are captured. So you can see even the shear. No, this is a composite section now. So you can see that means when you are modeling, it is not yet composite until you design. So it gives you moment capacity checks whether it is okay or not okay. You see all that, this okay, all these are checks that you look at. Transfer fatigue, even the fatigue resistant to longitudinal shear, it will give you, these are the ratios. This 0.24 is far low. Applied shear over the shear resistance is far low. It is 2100 versus 500. So that means you can still reduce this section to a certain point. And you can see shear resistance is given, longitudinal shear forces are all given here. Fatigue is also given here, and then it give you the fatigue loading. What are they considering? If you read your literature, there are all the references are all given where to read from. You can actually print all this and look at it, and then it will tell you that all these have been checked. The shear stress range for the connector is given. The damage equivalent factors are given. Equivalent constant amplitude range of shears to a 2 million cycle. Now, when you are reading about steel composite, the issue of million cycle, the number of cycle of the trucks are moving across your bridge always need to come in play. You get to know all the stress check reinforcement, stress check for concrete. You see that all that are taken into consideration. So this is exactly what we look at, and this is now where you get it, and then you give it now. Based on this, you can either give your CAD engineer to do the detailing, or so this is done for all the members. It's repeatable. It's repeatable. You see this member, C256. So this is only showing I, can be IJ, which will be too much. Both ends are taken care of, or only one end of the member. So this is how far you would go with the design. I've already given you this one. I share with you this component, the torsional stuff, from the model here. You go to bending resistance, and you get them all from here. This is where you print the Word document, and this is where you get the other. So this is how you would look at it, I think. This is briefly explain the design. What we shall do, and what I'm going to do a little bit of reading to check, is how those parameters relate, pick it, and then do another explanation. We just few touch up. So we may use the same example to discuss about that. So I think this is exactly what I could say and what I can share with you to round up that design aspect. So I think this is very important, but above all, please, I've given you the literature to read. More literature we shall share. Try to do a lot of reading, consult. I know some members are attending the bridge engineering training at the postgraduate level, certificate level, and also master's level. So when you do get those notes and handouts and get explained, so some of this now will be a very easy thing to follow. To get it done well. So I think with that, I think I call it a good evening, and I wish you the best. Please read and let us continue to share. That's it briefly about design. Thank you so much.